In this lecture, what we're going to do is start looking at using the A component from RGBA color. We're going to see it a number of times over the next couple of lectures, but in this one, what we want to talk about is using OpenGL's ability to composite or blend images together so that we could use that factor in a number of ways. One, to generate images in a couple of different images and then combine them in some way where one doesn't fully block the other. We can use it for image processing kinds of techniques. We'll also at the end make a few comments on how we can use these ideas to do anti-aliasing. Now, the basic idea is that you have we've been assuming that all of our surfaces so far have been opaque. So if we look at it from the perspective of having light and a viewer looking at some surfaces, then if a surface is opaque, it's going to block everything behind it. And that's the assumption behind the form of hidden surface removal we've been doing. At the opposite end is a fully transparent surface where all the light will pass through that surface. Translucency is really the more commonly used term, and it allows us to have somewhere between full opacity and full transparency, and simply translucency is 1 minus the opacity. So in OpenGL, when we use RGBA, the A is the opacity value, and if we want to talk about translucency, then it's 1 minus the opacity. Now it turns out that it's a lot more difficult than we might first think to deal with transparency and opacity in a way that's physically correct. And if you look sort of physically at what's going on, you could see that it can get kind of messy. I mean, suppose our viewer is out front here somewhere, and here's a reflective surface, and we have maybe some other surfaces that are reflective, or here would be a little surface that's translucent, that it would let through some light, but some light would be reflected backwards, and that might generate another bounce over here. And some of that light might be absorbed, the same thing for a little surface over here. So to try and model this kind of interaction, which is what happens in the real world, not only can it be very difficult, but it's also kind of a global calculation in order to figure out what a viewer is going to see. To find out what really comes out of this polygon, it depends on the polygon behind it, as does this one, and we can have all these more complex interactions like this one bouncing off the surface, bouncing back to the original surface, and back. It'll come through this third little piece of a surface. So for this one, we'd actually need all of the 3 polygons to be available. So you can imagine far more complex situations. So how do we do this in a way that's at least reasonable physically, but doesn't require us to have a global renderer like a ray tracer? So with that in mind, let me give you the model that's used in OpenGL, and I'll come back after that to see what are the problems with not having multiple polygons, or as we'll see, that our rendering will depend on the order in which we process the polygons, which hasn't been a problem thus far. So let's go back to the BitBlit model, but now what we're going to do is use BitBlit on RGBA values. So it's not going to be on a single bit alone, but it's going to be on a red, green, blue, alpha value. But the model will basically be the same, that we have something that we provide, which would be, say, a source color, which would have red, green, and blue, and A components. We'd have a color buffer that has at every location an RGBA color. And so now the writing model is that rather than have the source RGBA replace at each location in the frame buffer the value that's already there, that we have the same model we had with BitBlit, namely that we could read the value first and somehow combine it with the value of RGBA coming in, and that's called a blending function, and that'll get a new RGBA, which will be the one that we're going to place in the frame buffer. Now, what's going to make it more interesting is that we're going to take that RGBA that comes in, and we're going to blend it with some sort of factor. And it could be just a constant that says I want to take half of the source component and combine that with half of what I find here. Or what will be much more interesting and more flexible is to say that the source blending factor can be different for the red, green, and blue and A components. And that's where we get a lot of the kind of methods that will come out of this. Likewise, when I read the destination RGBA, I can apply a blending factor that might be different to each of the components. So what we're going to see for the blending function is that, I'll have this on the next slide, but the idea is that the red component coming in is going to be multiplied by the red source blending factor. That's going to be added together with the destination red multiplied by the destination red blending factor, and that's going to give me the new red that I apply, and the same thing is going to be true for the green and blue and the alpha components. So that's what we see here on the next slide. It looks a little ugly, but you can see that that's what all I'm doing is applying the different blending factors for source and destination, and potentially different blending constants for red, green, blue, and alpha, and I'm doing it independently for each component. And that's the OpenGL, WebGL model for doing blending. Now, how do you actually carry that out? It's pretty straightforward. It's a function that we have to enable, so we're going to enable GL blend, and then we pick with the source factor, the RGBA for the source, and the destination factor for the RGBA for the destination that we read. Now, in the model that we had back here, in principle, I could have anything I wanted for these four constants for the source and the four constants for the destination blending factors. But WebGL and OpenGL really only allows a certain numbers of those, and they're given mnemonics or names that you can use. I mean, they're the ones that correspond to the ones that are used most often. So the ones we're going to talk about, and the ones in WebGL are slightly limited over what's available in the full desktop GL, and you can look in either the Red Book, the OpenGL programming guide, or the WebGL programming guide to get the complete list. But the ones that are most important is GL0 says that you use 0 for RGB and A. 1 says you use 1 for RGB and A. So a source destination factor of GL1 and a destination factor of GL0 says just take the source RGBA and make that the destination. A transparent polygon, if you had the source as GL0 and the destination as 1, would simply say, I don't care what that source is coming in, I'm going to leave the destination alone. Now, the more interesting ones are these. Source alpha, which just says that you're going to use alpha and apply it to RGB and A, and you're going to use 1 minus alpha that you'll apply to RGB and A. And likewise, you can do the same thing with the destination alpha. You can have the destination alpha apply. Now, these apply to all of RGB and A, or 1 minus the destination alpha applied to RGB and A. Now, these are independent, so I can pick any of these to be the source factor, and any of these to be the destination factor. So now we have to decide, well, given these available factors, which ones make sense in a graphics context and in the physical context. So let's start with this idea. Suppose we started with a background that was opaque. Now, that was what we might set with clear, with the clear color. So if we set that to be an RGB, R0, G0, B0, and say, well, that thing is opaque. Nothing is going to come from behind what we originally set when we clear. We'll set the alpha there to be 1. So that's, you can think of that as if once we do the clear operation, that's the initial destination color. Now, suppose along comes a polygon where we've assigned those pixels to have R1, G1, B1 as their colors, and some value alpha 1. Now, if you look at now what we want to do, we want to combine this with what's already there in the background, R0, G0, B0. be 0, 1. And usually the first choice of factors would be to use source alpha for the source blending factor and 1 minus source alpha for the destination factor. Now, why do we do that? Well, if you use that, you'll get for the red. This will be the same for red, green, and blue, and actually the alpha component. If you look at what happens, if you look at the red that you're actually going to put in there, it's the source alpha times red plus the 1 minus the source alpha times the red that was already in there. Now that works correctly if the polygon that you're putting in is either fully opaque or fully translucent. See, if it's fully opaque, then alpha 1 is 1, and this becomes a 0. So and alpha 1 R1 is just R1. So all you do is you replace the destination with your new source. If the source polygon is transparent, then alpha 1 is 0, and so this term goes away, and this term becomes 1 minus 0, which is 1, and you leave R0 as the color. So it's correct on either end, and you can show pretty easily that what's happening here is an affine combination, and so you're always going to get something here that's between the source and the destination value, and you're never going to get something that's too high or too low. So that's kind of nice. So that people like to use this one, but there are some problems as we'll see. So you first can say that, okay, one thing you always want to be sure of no matter what factors you pick are that the RGBA components are always between 0 and 1, so you may want to do a check depending on what your blending factors are to make sure that they're clamped to be in that range. One of the biggest issues, and this is going to come up in a variety of ways later, is the biggest problem that you have with the traditional way of doing blending in OpenGL is that the RGBA values are only stored to 8 bits. So a lot of things you kind of want to do is that it would eventually cause problems because of the loss of accuracy. And the most obvious one would be to do something like this. Suppose I want to blend together n images, and each of those will have the same weight. And so I want to put them into the frame buffer where where the red, green, and blue components might be scaled by 1 over n for each one. Now that would prevent any RGBA value from being bigger than 1, and certainly they're not going to be less than 0 if I add them together. So I've sort of taken care of the clamping problem by doing that, but the problem is when you start dividing things by multiplying by 1 over n, and n is any kind of it starts getting large, you start losing all kinds of accuracy. So if you had, say, 256 images, as soon as you divide by 256, that's equivalent to a shift of 8 bits, and now you've completely lost your RGB&A. So this kind of problem sort of plagues you, and it's really due to the limited resolution for the red, green, and blue in the frame buffer. But if you don't do that, when you start adding images together and you're doing clamping, well, clamping will keep you from exceeding 1. But what will happen as you start adding in more and more images, what's going to happen is all of those components are going to start hitting 1 and then be clamped at 1, and so you'll notice your images are going to be completely washed out and look white eventually. And that happens with photography too when you start doing these kinds of operations. So you have a problem. Another problem, which is probably equally serious, is that these formulas, like the standard thing that you'll do up here is alpha and 1 minus alpha, turns out is order dependent. And that gets you in a couple of ways. So what we're saying is that if I render polygon 1, then polygon 2, and polygon 3 in that order, when the alphas are not necessarily 1, then what I see is going to depend on the fact that I did polygon 1, 2, and then 3. And if I rendered 3, then 2, then 1, I'm going to get a different result. And it's real easy, although a little ugly, I think I have this in the book, is that if you do this with just 2 polygons, you could see that the formulas are not symmetric with respect to polygon 1 and polygon 2. And you'll actually see that problem when you display them. So you can easily get something weird that looks like this, that here's a cube, and I'll do this example again. Now I'll show you this in interactive way, where this is the kind of thing you get. This just doesn't look quite right. That this front surface is translucent, and it looks okay here because you're sort of seeing the back through here, but then this bottom polygon over here may or may not be right. So it just looks, see what's happening to the orange one over here. It just looks weird, and the problem is that we did this alpha and 1 minus alpha blending, but the order is different. And what's even worse is that when you start rotating that polygon, then the order can be different, and you start seeing different kinds of things. So things can get really odd. So one way around that is to group the polygons in a way that sort of takes care of the opacity problem, where you have some mixture of opaque and translucent polygons, and then to do some sorting. So let's look at what you can do. Here. If you have some polygons that are some that are opaque, some that are transparent, what happens when you do the hidden surface removal? Well, the opaque polygons, we know they're going to block everything that's behind them, and once you put them in the depth, okay, and they'll affect the depth buffer, so that when a new polygon comes along that happens to be behind any of the opaque polygons, the hidden surface removal will take care of that. The problem is, what happens if a translucent polygon comes along? If it's translucent and you render it, what do you do with the depth buffer? The problem is that if you use that translucent polygon, you shouldn't use that translucent polygon to change the frame buffer, the depth buffer, because a translucent polygon, you can still see a polygon behind it that might arrive later in the rendering process. So what you want to do is turn off the depth buffering, or the hidden surface removal, whenever you have a polygon whose translucency is not equal to 1. So the usual way of dealing with that is to render all of the opaque polygons in the normal way with the hidden surface removal algorithm, and change the depth buffer. Then use this function depth mask, which is false, to make that depth buffer read only. Now, why do you do that? Well, one is it avoids this problem of translucent polygons changing the depth buffer, but you're still using the depth buffer when you render these translucent polygons. So if the translucent polygon comes along and it's behind something, it will then be recognized as being behind an opaque polygon and not rendered. If it's in front of an opaque polygon, then it will not replace the value that's already in the depth buffer, but it will contribute its color in a blended kind of way. Now, the other problem, which we had on this thing, is that the order does matter. And so what is generally done with if you want to get translucency in a physically correct and consistent manner, is you got to sort the polygons. And that is something we haven't done yet. It may be possible where you have objects with a lot of structure, like our cube. You can do that, and then you could render all the opaque polygons, then sort the remaining polygons and render them front to back or back to front, depending on how you want to use the alphas. But that'll give you consistency. On the other hand, you're not then treating each polygon independently from all other polygons, because you're having to have all those translucent polygons available to do the sorting. So even though you have this facility within OpenGL, WebGL, it's really difficult to write the code that gets it right in a consistent way. Or maybe a better way to look at it is that you have to somehow intervene to make sure that the order comes out correctly. Well, let's look at that example of the rotating cube done with some translucency now. Okay, so here it is. Let me get over here and turn on the rotation. So here it is, and you can see that some of those polygons, actually they're all translucent, but it's kind of order dependent. And let me toggle hidden surface removal. Here it is without any hidden surface removal. And you can see what happens here. If I turn on hidden surface removal and do it correctly, then things come out a little bit better, as you can sort of see here. You're not getting kind of the oddities that you see over here. This is on the website under Chapter 7. It's called something like Translucent Cube or T-Cube. And look at the code and see the kind of things you can do with blending. Okay, we'll also come back and talk about how this, at the end, about how this interacts with the HTML5 canvas, because that is a little different with WebGL than it was with DesktopGL. Okay, so let's come back to this, and now let's look at a couple of things that we can do with blending and compositing. Okay, one is to add something like fog, which gives you, one of the things that happens with images that you create and are supposed to look realistic is there's no there's no atmosphere, and so things look clear, out from right in front of you out to infinity, and that isn't quite right. What you need to do is to make them look a little more realistic is add some kind of a fog effect that's the effect of having an atmosphere that isn't perfectly transparent. There used to be an old fixed function OpenGL. There was a fog function that allowed you to blend what you were doing with a fog color. This is actually a very old technique that was used in old systems that were non-raster. And what the idea was to render things further away, dimmer than things close to you. Think about somewhere you don't have polygon fill, and all you could display was wireframe objects, complex wireframe objects, and if everything displayed in the same brightness, you really couldn't tell the three-dimensionality. But if you took things that were further away from the viewer and you dim them, which is equivalent to saying there's more fog between you and them, then you can get some very realistic displays without having to use raster graphics. So this is where this kind of fog idea came through. There were three kinds of fog that were available in fixed function OpenGL. Linear, which was called depth queuing, which was the technique that goes back to the old pre-raster systems. The ones that were more physically realistic were to use either an exponential or a Gaussian to determine how much of the fog to be blended in as a function of how far you were from the viewer. Here's a little picture of what the fog functions that were supported. So here's distance from viewer and how much you attenuate the object and add in 1 minus that of adding in the fog color. So you can get smog colors, you can get fog colors by doing this. Easy to do yourselves without having the function that has been deprecated. Okay, now the remark I made a few minutes ago about compositing in HTML. This is somewhat different than what is done in desktop OpenGL. In desktop OpenGL, if you don't enable blending, it doesn't matter what you do with the A values. They're just not going to be used. It turns out in WebGL, and I was tricked by this at first, was that if you set A to something other than 1, it does matter. What it does is it multiplies that value, assuming it's between 0 and 1, it multiplies that times the red, green, and blue components. So if you set A to be 0.5, regardless of whether blending has been enabled or not, it's going to be equivalent to setting the R's, the G's, and the B's to 1/2 of the values that you specified. And so you'll see them if there's nothing else going on. You'll see those colors as being faded from what you thought they were. Now there's a reason for that, and the reason is that that WebGL, it operates within the canvas element in HTML5. So anything else that you're doing on that canvas is going to be displayed. And what this does is give you the flexibility of blending what you do in WebGL with what some other application might do. One example that would probably be of interest is if you wanted to add some text on top of your images. We don't have text primitives in WebGL, and one of the reasons that it shouldn't be a problem is you have all these other ways of getting text up on the canvas, from simply writing the text within the HTML5 to using some more complex application. So this allows you to blend in things from other applications with what you do within WebGL. But be careful of that, because I really was tricked by that, and it took me a while to figure out what was going on. Now let me finish by just saying a few things about aliasing, because it's going to come up in a variety of ways. It was something that blending it's something that blending still can be used to ameliorate. So let's start with this idea, that if you looked at what would it be an ideal raster line, and the reason I'm calling it a raster line is that a mathematical line has length but no width, and so you would never see it. What would be the ideal line to display in your frame buffer? Well, we could argue it should be 1 pixel wide. Some frame buffers will let you actually do less than that and have half and quarter width, but generally the idea is that if I were to draw this ideal raster line, it should be 1 pixel wide. Now the problem is that line, if it isn't going horizontally or vertically, is going to lie over multiple pixels for a constant x or a constant y. So here you have a little piece here that if you cut off sort of 1 pixel wide here, it would be spread over potentially 4 different pixels in the frame buffer. And if you use the standard FAST algorithm, which even though we have yet to talk about implementation, you can sort of have a very simple algorithm, which is for each, as I go across in this direction in the frame buffer, for each x on this line, put in the closest y. So if you're closest to this one, I would fill in this pixel, and as I moved over an x, I'd fill in this pixel fully. And if all you can do is just fill in 1 pixel for each x or 1 pixel for each y, you're going to see that jaggedness for everything but horizontal or vertical lines. And this is the jaggies or the aliasing problem, and it's sort of built into the fact, because you're trying to render into a discrete frame buffer and you can't really get a 1 pixel wide line. Now what you can do that's a little better is to say, well, why don't I, instead of saying all I can do is render 1 pixel for each x or 1 pixel for each y, why don't I say I can put a little bit of color of its color in here, a little bit of its color in here, a little bit of its color in here, and composite that. This is where the compositing and blending comes in, and composite or blend that in with the background or whatever else is going on. And that's a standard technique of anti-aliasing with what's called area averaging, so that you look over each area and try and decide what to do. Well, mathematically, that can be a little trickier than you might think, because here you could sort of argue, if I know this line and I know exactly where it goes, I could say, oh, this fraction of this pixel is covered, so I can put a little bit of blue in here, and here I can put, for this line, I can put a little bit of blue up here. But the problem is, what happens if these lines overlap? Then the correct amount of blue has to account for this overlap kind of area. And if you think about this in sort of probabilistic terms, or if you've taken a probability course, you get a little formula that says, on the average, I should take off the average overlap over all of the lines that might fall into this little pixel. And so I get something that might look like this, and say use the average, the alpha 1, this area here. See, so what the idea here is, now we use the alphas to be the percentage of that color that should be put into that pixel. So we use, to account for the potential overlap, we subtract a little bit off of the products. So alpha 1 and alpha 2 can't be bigger than 1 because otherwise then they would occupy the whole pixel. And the average overlap, you could argue, is alpha 1 times alpha 2. And this factor will always be between 0 and 1. So that's kind of what you'd like to do. You could have done it in the old OpenGL with functions that were supported. Well, let's say what was supported and not supported. Right now in WebGL, there's no support for this kind of anti-aliasing at all, although I expect we'll see that in the future. Some of the hardware will automatically anti-alias, so with high-resolution displays with really good hardware, it's less of a problem than it used to be. But if you do want to do some anti-aliasing, then the way that it was done was you enabled blending, and you used alpha and 1 minus alpha as your source and destination factors. And this you can still do, But what is in the full desktop OpenGL are this function using enable in 3 different ways to smooth lines, smooth points. Because if you just generate a point primitive, it's going to come out as a pixel, a square pixel. You would probably prefer that to be a little more rounded by spreading its color over multiple pixels. So anti-aliasing of points makes them look a little more like little circles, and you could smooth triangles separately by turning on enabling polygon smooth, line smooth, or point smooth. But as I said, this is not yet in WebGL, although I expect it'll probably be there in future releases. But an awful lot of this, as we'll start seeing in the next couple of lectures, you can wind up doing yourself within the shaders. So now what we're going to do is look at some applications where we actually start putting it all together, using textures, using blending, and do some imaging types of operations.